To be honest, I think I had myself at the point. I'm sorry about it. I just forgot it. Probably I have in my, OK, thank you very much. Yeah, for this. OK, so, all right, yes. OK, as promised, I prepared a code which deals with the scalar perturbations for the following theory. For lambda CDM plus a fluid. OK? This one, we will see that the example is non-trivial, because we will see that there will be choices that we will make, and these choices will lead to maybe some different, apparently different answers. We will see in real life, oh, I don't know in real life, but anyhow, we will see in real calculations what we have discussed about this Lagrange multipliers and the way how to reduce the degrees of freedom. Now, so the code is very similar to the one we did on Saturday. Okay, the idea is essentially the same. Here you see, I again start with this comment here, which clears all the memory in Maple. It's not really necessary, but anyhow. Then I use this Maple built-in differential geometry code, and also the Maple built-in tensor code. And I define my manifold having this, for dimensions with variables t, x, y, z, and I call this manifold M. Then I introduce the metric tensor, and as you can see, once I write it in terms of a matrix, it looks like this. As I told you last time, I am considering here a wave, okay, propagating only in the x direction. Because we are in linear theory, the wave and the equations are linear. The coefficients of the equations will be purely time-dependent. So the wave propagates in a homogeneous and isotropic background. So no matter which direction you want to choose, that's perfectly the same. If it would not be the case, it means that the x direction will be special. Okay? Why do I do this? Do I need it? No. I could put t, x, y, z. But my code will be more heavy for no big reasons. Okay? So because I know that the modes will decouple, possibly I study a simple mode. Okay? So I'll try to do this one as much as possible. So then in this case, so this will be, so I use that part of the blackboard to write down stuff. So remember the metric was looking, I wrote the metric as this one. Minus 1 plus 2 alpha dt squared plus twice di chi dt dxi. Notice that I neglect the vector components because I'm studying a tensor here. Sorry, the scalar modes, okay? Plus, then we will have a square 1 plus 2 phi delta ij plus twice di dj gamma. And I think that's all, right? Because I also neglect the tensors. Now notice that in the way I wrote it, there is no gamma. Okay? So I know that I can do this, so I have fixed Xs. Okay? So gamma is 0. Okay? At this moment, notice that phi is still here. Sorry, alpha, chi, and phi is still here. So I have not fixed the gauge so far for Xi naught. Okay? One possibility, so gauges, one possibility would be to set phi equal to 0. The other possibility would be to set chi equal to 0. Okay? Longitudinal gauge, flat gauge. Alpha equal to 0, no. All right? Because it doesn't fix completely the gauge. Okay, so as you can see here, there is still a gauge degree of freedom, which is alive. I choose it to be like that, okay? Okay. So let me evaluate. So G is given by this. Notice that in Maple, G is not by default symmetric. So I had to impose it to be symmetric. As you can see, this derivative of chi with respect to x will have is multiplied by dt dx and dx dt. This make it symmetric. Okay? Dx dt is the component xt. Dt dx the component tx. Okay? Now this is ds square. Okay? Now I am introducing there the g as a tensor. Okay? So the tensor will be dt dt tensor dt. Okay? Does it make sense what I'm saying? This is ds squared. ds squared is a scalar, right? So I have to introduce g alpha beta as g00 dt dt plus and so forth and so on. Actually, I should have write g alpha beta dx alpha dx beta. Okay? Where this is now, these are forms. No, this is the one form, right? So then, what I wrote there, this is dt dt, g00 will be minus 1 plus 2 alpha. And then I wrote there di chi dt dxi plus dxi dt. So this makes it symmetric. Okay? And because chi is only a function of x, we don't see dt dy and dt dz. Okay? If something looks not clear, please ask me, because for me this is, sometimes I give for like granted that everything is clear, but maybe no, okay? So please let me know whether, okay. Okay, so then we will have this kind of metric. Here you see the trimetric is diagonal. And as you can see, I introduce everywhere the epsilon parameter that I was telling you. This just to make the Lagrangian become a function of epsilon. The fact that I put epsilon with the same power means that all these perturbations have the same magnitude, more or less. Okay.
That means now you are dealing with your perturb metric.
Yes.
Okay.
Now the metric is that one.
Yeah,
if you want this one. This is
but
one.
with perturbation.
Yes.
Near perturbation.
Exactly. So if you put epsilon to 0, you will go straight to freedom limit limits work.
Background metric.
Background metric. But strictly speaking, G is not the background metric. G is this one.
Yeah, G is this one. Okay.
Now, for example, here you see I calculate the determinant. And remember that the determinant for the background was just a to the 6. Actually, minus a to the 6. Yeah. Okay? Now you see that the whole thing became a horrible expression with terms in epsilon cubed and terms even in epsilon to the fourth. Okay? And that's just the determinant of the metric. It's not the Riemann tensor. Okay? All right. So this is another way to say that, in this case, this kind of computer software is really handy. Okay, then I do the inverse. I put this column here just not to show you the result, because you would have a heart attack or something. Okay, maybe after some 1 hour of relaxation, you may see it, but now you would get a heart attack probably. So no. And the Christopher symbol, I put another column here. Okay. Okay, so now, and now you will see many columns. I will not show you anything else. The determinant was already enough to give you an idea of the complication thing. Now, with this one, I calculated now the Riemann tensor. And notice, as I said, that I already made a simplification, because I imposed my wave only to propagate in the x direction. If you put here other terms here, and this one function of t, x and y and z, you may imagine that the whole thing becomes even more complicated. Then it's a question of how Maple handled these huge expressions. That's why, this is my little help to Maple, I impose this to be only a function of x. Okay? So I am focusing on a way which is propagating the x. You could have chosen a way propagating the y or the z. That's totally arbitrary. Okay? Okay, then this is a Ricci scalar. Now, it's almost done because remember that I want to write down general relativity in the presence of cosmological constant. So the action for the Lagrangian for general relativity is already there, because the action will be this, no? Well, square root of minus g. So this would be the part that is really general relativity plus a cosmological constant. Now, lambda is a constant, so we don't need really to care about its perturbation, because it's a constant, right? But now, remember that I calculated the determinant of g. That was the only thing that I showed you so far. Right now, I have calculated the curvature. So now, the Lagrangian for the gravity sector is over as a general function of epsilon, which is a monster expression, actually. Probably, if I try to show you, it's possible that Maple will break, because then it has to handle with memory how to write down in a beautiful way is a result. Okay?
So you are imposing two gauge functions, flat and
No. Only one gauge condition. Gamma equal to 0. I didn't say anything about other fields.
But if you take the other function, means epsilon is a function of xy, means t x y z, then also Maple can do, no? I think.
Yeah, Maple can do.
Yeah.
GR can do.
Yeah.
When you do not GR, very high chances it says, you do it, I don't do. It never happened that Maple replies like, you do it, I don't. But maybe. Yes, so yes, I mean, in this context, probably I could leave the whole thing. But really, it's not necessary. If it would be necessary, then I completely agree, actually. But it's just overloading something which is not needed. Because
it will not alter if you.
Yeah, because we are going to, because we are studying linear perturbation theory.
Yeah.
Suppose that, as I did in the past, suppose that somebody wants to study non-Gaussianities. So non-Gaussianities means that interaction between different modes. Okay? Then one needs to go to third order Lagrangian. And now, this is not true anymore, actually. This beautiful simplification would be not general. I will oversimplify the system, and will not be a good way to do it, actually. So if I had to study, say, non-Gaussianities, I have to introduce more variables. Okay, so that part of the Lagrangian is fixed. Now we have to remember that I had to add the other Lagrangian. I said I want to do a fluid, and then the Lagrangian for the fluid is this one. If you remember, we have a square root of rho, which is a function of ns, and then minus g mu d mu L plus theta d mu S. As I told you last time, I'm neglecting AB because they give contribution to vector modes. So this will be the general one if I want to discuss the scalar modes. Right. Now, having said this, so now I am defining the field L. This is a scalar. And I will set that L is a function of time, LT. So this is just notation. LF means this is field L. Okay? LL would be just the time, the background component, plus epsilon dLLTX. Okay? Of course, I cannot put Ty. That would be, it's like I study propagation for one of the mode along the x and the other one along the y. They will be completely decoupled. Then I would lose information. So if I say that I am studying propagation in the x, then all the fields I have should propagate in the x direction. Otherwise, it would be nonsense. Okay? Okay, so then here I have defined my scalar field. And that scalar field are very useful. Are very easy to introduce because it will be just background plus delta of that field. I don't have components to take care. Now, this is the covariant derivative of L, because, of course, I need this. Partial derivative of a scalar is equal to the covariant derivative. I use here covariant derivative because when I do this, automatically Maple understands that now this DLL becomes a tensor, a one form. And you will get this, no? Because you will have a time component times the partial derivative with respect to time times dt. This is the form dt, plus the derivative with respect to x of dx. Okay? Good. Then I do the same thing for the entropy. Now, you notice here that I put s to be a function of time. We know that at the end, s will be constant. Remember, s is a constant. But so far, because if I already say what is the answer, then I know already the problem. The fact that s is constant should come automatically from the equations. The only point I put is that homogeneous and isotropy, s must be a function of time. On the background plus epsilon ds. And I do the covariant derivative of this field, and I get this one. Then I introduce the field theta, which is here. And again, background plus perturbation. Now I do something which is slightly non-trivial. Remember that I had my J mu. And remember that, if you remember well, n was J alpha, J beta, G alpha beta divided by G. Okay? This n here is this object there. S we already defined. S is the same scalar that we had defined there. Okay? Now we had to define this G mu because G mu is also a necessary ingredient for n. And J mu, this is a 4 vector. So a 4 vector will have the 0 component, which will be a scalar. I will have dj plus a purely vector component. But this one I forget because I'm studying the scalar modes. It's also possible, let me see if I did it. Yes. So I divide this one by a square. Okay? The reason why I did that one possible reason is that if you take J mu to be minus J0 and Dij, okay, when you raise the index mu up, at the linear order, it will be this one. Can you see it? Because at the linear order, any other correction will be second order, actually. J mu nu J nu, no? This is this one. So then, if this is first order, this one will give you some. And of course, when I say J0 here, there will also be correction, delta J0. Okay? Or if you want, this is just a Fourier definition. Whatever J, I recall it to J divided by A squared. You know that I can multiply by any function in the background. So I introduce this dj. This will not be fundamental, okay? You can also write your own code without the A square. You will see that you will not change anything. Okay, so that's how I define J view up. You see, I have J0 time plus dg0. That will be the 0 component, because this is multiplying the basis of the vector, dt. And then, as I said, I will have di of this dj. Can you see? This one only becomes dx because my perturbation is depending on x. And then I multiply by this object here because this must be a vector. So this is the basis of the vector, actually. Notice this a squared is just a function of time, so you can put it inside the derivative of x. So this still means that that part is the gradient of a scalar. Okay? All right? That's all. I think I defined everything I had to define for. I defined all my fundamental fields in my matter action. So what I do here, because I had to calculate this object here, and G alpha beta of J beta will give you J alpha down, I calculate this J down by lowering the indices of J view up with a metric G. And one means, so I have J view, I have J mu. So I had to lower the first index, J mu. So I had to say lower the first index, mu, with the metric G. Okay. Then I define my number density. And you see, this is the contraction between J view up and J view down, divided by the determinant of the metric. And then I take the square root. Notice that when I do this contraction here, then Maple understand that this object here has become a scalar. So J view up, J view becomes a scalar, right? So then this one is really a scalar. I can divide it by another scalar, and I take the square root. For Maple, this is not anymore a tensor. N becomes just a function. Okay, so in the following, right, so this is the first non-trivial step. So in the end of the day, at the end of the day, we have to write down our results in terms of some fields. Okay, so I will try as much as possible to write down the final results in terms of physical fields, fields that it's easy to understand their meaning. One of these fields you may expect to be delta rho divided by rho. Delta rho divided by rho will be rho is the background here, and delta rho is how much delta rho differs from the background value. I divide it by delta rho so that this object here becomes dimensionless. Okay? So linear perturbation theory holds as long as this quantity is always less than 1 in absolute value. When this object will be order 1, linear perturbation theory will break down. Okay? That's something that we should sometimes remember. We had to use some fields for which it's easy to give, 1, a physical interpretation, 2, possibly to understand immediately when linear perturbation is breaking down. And for this aim, I will use delta rho divided by rho. There is another field which is also useful to do that, actually, and that's the field phi here. Because again, when phi will be order 1, you may expect that this swing will be of the same order, actually. And phi, as you can see, is dimensionless. Okay? So one way is, okay, I will try to put my results in terms of phi. That field sometimes is called curvature perturbation. Okay? That field is used very much in inflation, say. This field is really there only if matter is present. Okay? Right. So what do I do here? I want to define this one. I know that this field here is not a fundamental field. I don't have this delta rho in my Lagrangian. But I know what is rho there. So what I do here, I say, okay, take rho, which is a function of n, which was defined before here, and, oops, I didn't change this part. And so consider rho, which is a function of n and s. S was this, right? The S field is this. S plus epsilon delta S. Very well. Then you expand, make a Taylor expansion up to order okay. For the people who do not know Maple well, so I'm going to say, what does it mean, that object there? So if I have f of epsilon, and if I want to say, Maple, do a Taylor expansion, I do the following. I say series of f, and make an expansion in the term epsilon, according to a parameter epsilon, and I have to put a number here to which order I want to do. For example, let me put it 2. When I say 2, it means that Maple will do f of 0 plus df over the epsilon 0 epsilon plus order epsilon square. So it will calculate up to this order here. So one order less. Okay? And that's exactly what I want, because I want to know what is delta rho at the linear level. So after I do this expansion, I will say, Maple, please transform this series into a polynomial, and get the coefficient of epsilon. This will be my delta rho, because this will be rho the background plus delta rho. Okay?
Means you are considering perturbation in rho.
Exactly. So I don't know what, I know how rho depends on ns, so I can write delta rho in terms of my ns variables, which were function of j0, j mu, whatever. So when I do this, so you see I do this series expansion, I say convert into a polynomial, I expand up to second order, and take the coefficient of order epsilon. And then divide it by the background quantity, rho. If I do this, I get that. Now let's see what is this. Wow, this looks complicated. It is. It's a bit complicated here. Now this is delta rho. Delta rho will have a term which depends on delta S. And you recognize this one. This will be like temperature. If you remember, delta rho is d rho over dn, constant entropies dn, plus d rho over ds, constant n ds. So this will be the temperature, Nt, on the background. And this, everything else is dn. Yeah, is the perturbation of the number density. So you recognize this is the term in ds, and in fact, this is the temperature actually here. D rho over ds, and I divide it by rho. Right? This is d rho over ds in maple is this, d2 over rho. Because rho is a function of two variables. So d2 means derivative with respect to second variable. So this is a partial derivative of rho with respect to s. And then it's divided by rho because I am defining d rho divided by rho. So I divide it by rho of the background. Okay? So this part here is exactly this one. After dividing by the background density rho. Okay? So everything which is left is dn divided by is this other part here. So as you can see, there is the d1 rho, which means the partial derivative of rho with respect to the first variable. Partial derivative of rho with respect to the first variable. Then divided by j0. So this will be my dn, d rho dn divided by rho. Okay. Now, why do I want to do this? Okay. The reason is simple. As I said, I want to express my result in terms of this very nice variable. Because people say, okay, this was, for example, the dj naught was the perturbation of this vector here. What's the physical meaning of this? I have no meaning. I have myself no idea. But I know what is delta rho divided by rho. So this will be used for, later for me to make a Fourier definition. Instead of dj0, I will use d rho divided by rho. Okay? So I want to hit you here with the fact that I can do Fourier definitions. And Fourier definition are useful because maybe I can express things in terms of some very physical variable. Because how do I tell the astronomer, look, did you find constraint on dg0? Say, what are you talking about? What have you eaten this morning? Okay. If instead I tell him, look, I want to know some bounds on d rho divided by rho, he will say, okay, I understand what you're talking about. Okay. All right. So then I will define this equation here, equation for dr, to be minus dr plus this, and this will be 0, this equation, because this is my definition of dr. Right? Dr was this thing, so that's exactly this object here. So minus dr plus this will be 0. And I will use this equation later on to replace dj0 in terms of dr and the other fields, of course. Okay? So I will then replace dj0, which is really a bit unphysical meaning, with a very physical meaning dr. I could have used maybe delta n. That's another possibility. But delta rho is even more, people understand immediately what it is. Okay, fine. Then I write down my action. My action is the following. So I have a general relativity, m Planck square divided by 2 times the square root of minus g, Ricci scalar minus 2 cosmological constant minus the square root of minus g times rho, which is a function of n and L, and S. This is the S variable. And then I had to do minus g mu, this object here. So minus g mu up contracted with dl, and minus L theta, this theta field here, j mu d mu S. So this is the Lagrange that I wrote down there. Okay? Using the variables that I use. Yes?
When you're calculating rho with respect to first or second variable, this rho is dependent on n, right?
Yes.
So you have defined n as j0 or aq.
I define 0 as I define n as square root of j alpha, j beta, g alpha beta divided by j. This was my definition of n. Okay, so you say I could have. Okay, please let me.
We have already defined n, right?
This is delta rho divided by rho.
No.
Here.
Expression. This n is different from this one. Then in the ninth expression.
This is the same, right? And n is the same. So what I'm saying here, I'm considering this thing here. I am perturbing this object here, where n is given by this, and s is s of time plus delta s. I cannot cheat. N will be this monster variable there. S will be this scalar with perturbation. I cannot cheat. So I cannot put, so this rho must be exactly my function of n here, and s plus epsilon delta s. And then, okay, this is monster expression. If I want, if you write this one, we will get a monster expression. But I don't care because I need only the order epsilon. Because I only need to know what is delta rho at the linear level. And then you will get this one. Ping, ping, ping. Notice that this comes exactly because I have metric. Otherwise, it would be impossible to get it. This phi comes from the metric. Of course, this term here will be missing in the flat gauge, for example. Okay? All right. So, for example, here, this would be delta n. You see, I expand n at the second order. It will be n of the background, which is exactly this n of the background here. And then this will be delta n. And as you can see, you get this 3 phi minus the J0. Okay. So, fine. So we define the action here. So now I evaluate L0. Well, L0 is the action when I evaluate it on the background. And we will get this one. This is very similar to what we have gotten last Saturday, with the difference that last Saturday I didn't introduce this term here because I was assuming from the beginning S was constant. But this time I relaxed this thing. I want to show you that you can get everything from the equations of motion. So in the following, I said we have L1. So L1 is the action, the Lagrangian, I should say, the Lagrangian expanded at up to order second, but only take the coefficient in epsilon. So this will give me, remember that yesterday I wrote that L will be Ln 0 plus dl over the epsilon equal to 0, epsilon, plus 1/2 So before I showed you L0, this will be L1. And this will be L2. And L1 is only this. Because I do the Taylor expansion, and then I tell him, please get the order epsilon, the coefficient of epsilon. OK, so we will get this one. Did I show you what it is, this? Maybe here. OK, now this is the action at epsilon order. Nobody is having an heart attack. That's good. Means you already saw something worse in your life. OK, so now, so you see, and this is, OK, let me show, remember that the SEC, what we should expect to have in the results. OK, we have terms in phi. All terms are linear in the perturbation, OK? Otherwise, it would be a mistake. OK, you have this term, which is linear in perturbation, times background quantities. Background quantity times alpha. Here we have phi again, alpha, phi, alpha. This is all standard. Here we go. Here we have a time derivative of phi. Okay? And we know what to do. We have to integrate by parts this time derivative, such that this term will combine with this kind of term. Now we have here the time derivative of alpha. This is the second time derivative of phi. This is phi, alpha, ds, whatever. Aha, now we have the second derivative twice of chi. Now what is that term? The term there is the following. That's the partial derivative with respect to x of chi. Okay, times a function of the background. Now remember that we said from the beginning that chi was only propagating into x. If you would have allowed chi to be a function of y and z, what you would have would be this. So this will be the Laplacian of chi. Because the Laplacian is isotropic. We cannot have anything else. Would be if you get something else, we don't mistake something. All right, so that's, again, we neglect this part because this one already gives me the information that I need. And you see that on doing integration by parts, this term will disappear because I will have the Laplacian of a function of time, which is 0. OK, so what I do now, OK, so that looks complicated. So now we start to do integration by parts to make it look simpler. Let's see how we do this. You see what I do here. This command you already saw last Saturday. I hope you didn't forget completely. But you see, for example, now I say here there should be a term which is time derivative of chi, but 2 derivative in the x. Probably a term like this should be here. I don't know whether. Here we go. This kind of term. Okay? So I have to do partial. And you see that the coefficient in front of it is a function of t times this kind of thing. So I had to do the derivative of this object in terms of x, and maybe even time, actually. No, I left it as d over dt. This is correct. Then I have this second derivative of phi with respect to t. And then I had to do 2 integration by parts, d of cctt times phi. Does it make sense? I'm talking nonsense for you. I am doing integration by parts by applying the rule that any time that Maple finds a function of time times the second derivative of time of phi, it will transform it into phi times the second time derivative of c. And the same thing here. This is the second derivative in x. I will do the same. Okay. Now, the action probably simplified a bit. Let's see. Not so much. Not so much. But don't lose hope. Okay. Now, then, in this Lagrangian here, I probably still have some other. You see, this is a second derivative of alpha with respect to x. So you see, I integrate by parts. And second derivative with respect to x of chi, so I also integrate by parts. And probably that's all. And this action probably looks a bit simpler. Slightly simpler. So now you can see that I have left with time derivative of phi, time derivative of dl. dg0 is fine. So probably now I have only to do partial integration by parts in t. So for example, probably I have, this time derivative of alpha. So I have, any time Maple you find a function of time times the derivative with respect to time of alpha, transform it into minus the derivative of that coefficient times alpha, and so forth and so on. Then action, collect. And this is the most you can do, because what happens now, you see, I have a coefficient that multiplies alpha. I have another coefficient which multiplies phi. I have a coefficient which multiplies delta L. I have another coefficient which multiplies delta J0. I have another coefficient which multiplies delta S, another coefficient which multiplies delta theta. I cannot do anything else. I don't have any time derivative of x derivative of the fields, actually. So all this must reduce to equations of motion. Because this is the equations of motion is when I take the variation in linear order and then I put it equal to 0. Okay, so the first way we recognize that we knew that J0 is a constant. Okay? Now, if J0 is a constant, this means that S will be constant also. Okay? So here I put that J0 is this one, S now is a function of time. So now I am, the equations of motion for the background gave me some information. Now I am implementing that information. I am say, okay, then my background will be this. Before I didn't know, before I knew. But anyhow, I suppose I didn't know, and then I will apply it. Now let's see how, then we have this equation of motion for delta S, this equation of motion for dj0, and then the other two equations. Now you notice that this equation is L dot is equal to mu. That was the equation of background we already saw, and minus and mu is 0 over dn at constant S. Okay? So exactly this is what we've written here. So L dot is equal to minus the partial derivative of rho with respect to n, which is exactly minus mu. Okay? So here I impose that equation of motion and say, okay, so L is this function here. Is the integral, because I can do the integral of this function here. And then I get the same thing for delta S. Delta S was giving me the other equation. If you remember, the other equation was theta dot is equal to T. And T is equal to 1 divided by n d rho over ds at constant n. And remember, because this comes from this one, no? From the first principle of thermodynamics, this is mu dn plus nt ds. Okay? All right? So the partial derivative of rho with respect to s is actually nt, so t will be this one divided by n. Is it clear? We already saw, to be honest, this kind of thing. Okay, so now then that's exactly what I'm doing here. I am defining my theta to be theta dot is equal to temperature, because you see this is the second derivative of s with respect to s, and I divide by the number density, n0 a cubed. Okay, then my linear action becomes only proportional to alpha and phi. So this will be the Friedmann equation, and this will be the second Einstein equation. In fact, this is the coefficient. I take the coefficient of alpha. This must be 0, and I divide it by a cubed, which is still 0, and we get exactly the Friedmann equation. 3m Planck square times the Hubble factor square is equal to rho plus lambda mass Planck square. These are Friedmann equation in the presence of a fluid and cosmological constant. The second Einstein equation, you can see, will be this one. And as you can see, this is n times d1 over rho minus rho. This is a pressure. This is how we define the pressure. Okay? Pressure is mu n minus rho, and mu is d rho over dn at constant entropy minus rho. That's the pressure. Once we have the fluid, which is a function of ns, this object here is the pressure. And this will be the pressure of the cosmological constant, which is negative, equal to minus rho. Okay, then I say, Maple, I will implement my equations of motion in the Lagrangian by solving for the cosmological constant. Okay, so solve E1 for the cosmological constant. The solution, I will call it with this name. So this is the cosmological constant solved when we impose the Friedmann equation. And then I say, okay, hold on a second. This is a constant, so if I take the derivative of both members, I will get 0. Okay? So I take the derivative of this object here, and this one must be 0. Okay, and then I say, very well, so this is the derivative of this object here. And then please, Maple, solve this equation, because this must be equal to 0, for the second derivative of A with respect to time. Okay, this will be the second derivative of A with respect to time. So why do I do this? Because when I will write my action, I had to say to my perturbation variables, look, you are on a cosmological background, which is defined by cosmological constant and the fluid. So anytime you will see A double dot, please replace it with this expression here, because this is my background equation. If I don't do it, then the perturbations are not perturbation on that background. Okay? All right. Then I say, very well, Maple, you found this equation here for the second derivative of A. Please replace this equation and L in the second Einstein equation. And I get 0. This is just to be, for consistency, I should get 0. Okay? So in other words, I could have solved for the second time derivative of A from the second Einstein equation. What I did here, I just said, OK, the Friedmann equation is correct. This is a constant. I derive with respect to time. I find the second derivative of acceleration. Very well. Then these two equations inserting in the Einstein equation should give me 0. Otherwise, I would get some inconsistency.
That means you are using a background.
Exactly. Very well. Now we define the background, and we are ready to finally see the action L2. L2. Now we will see this object here, which is the thing that we have discussed in the last 2 days. Remember, we said, what should we expect from this Lagrangian at quadratic order? OK, now we are calculating this one here. And the way I do it is always the same. I say now, please, Maple, take a Taylor expansion of action, expand it in terms of epsilon up to cubic order, and then please get the coefficient in epsilon squared. Then transform this one into D was this differential operator. Okay? So Maple say dx over dt is d of x t. This is just a way how to write down derivative. I ask, please, Maple, use that way of writing derivatives. OK, so he did it here. OK, you see, it took not much time. Eh? Look, I'll do it again. 2 seconds. My computer is not bad, but it's not the monster computer anyhow. So 2 seconds, it's quite good. Now, very well. Now, remember that when even L1 was already a bit complicated, L2 will be much more. What we have to do is to do integration by parts and remove Lagrange multipliers so that it becomes simpler and simpler. OK. I really want to. So is there anybody with heart problems? OK, I'm going to show you. Tac. You see, the command was up there. I don't know exactly where there is the command. But for a second, let's see what we get here. We get a term which is alpha phi, which is still OK, times a background quantity. This is the first derivative, so this will be mu something. Now we have theta del ds, alpha ds. This is all fine. This is phi dg0. This looks very, very phi squared. Probably there are lots of them. Each term seems to be OK, but there are lots of them. OK, phi squared, we get, so this is the second derivative of phi with respect to x squared. So this term, that term there is something like this, d phi, di phi. OK? We should get it from this kind of term. OK? And when phi is only a function of x, it will shrink to this one, the partial derivative of phi with respect to x squared. OK, we have a term which is ds dot times d theta. We have a dl something else. OK. Now what do I do? Now what I said yesterday, this is already said yesterday. Now I will say, OK, not only the fields are function of t on x, but I will also assume a waveform, which is a cosine in kx. So what I'm doing here, I'm doing like a Fourier expansion, OK? But only keeping one of the mode. Because once more, at the linear level, all these Fourier modes will decouple from each other. And the reason why they decouple from each other is because the equations, the wave will feel a homogeneous and isotropic universe. So different k, different modes can never communicate with each other. this must be, because again, this will be oversimplified. I don't need to do this. For example, I could do the following. And later on, I will discuss a bit about it. I could have done the following. So Maple, please write chi into this form. D3k chi tilde of t and k e to the I kx. This would have been a Fourier transform.
Yeah.
Okay? But now, so the equation of motion for chi will be linear. Okay? So I may have like an nabla square chi plus something else plus chi plus. So when you write down this object here, you will see that you will get d3x times maybe minus k squared chi plus chi tilde times e to the I kx. So this thing factorizes. So then you see each k will completely you don't see any coupling between k1 and k2. Okay. So in particular, if you integrate over d3x, which we have it in our Lagrangian, this will give you, So no, I'm sorry. When you find your equations, okay, no, this is not correct. So the equation of motion will be something like this equal to 0, okay? For example, then you do this stereo expansion equal to 0, and because this must be true for any k, you have to set this one to be 0. Okay? But then you will see that each mode will have its own equation of motion, completely decoupled from any other k. If that will not be the case, it means that there are some problems here. For example, maybe you have some function of x. Then it will not be the case. But no, we know that this coefficient here will be at the most function of time. Okay? So among all these possible Fourier decomposition, I know that all the modes decouple. I consider a particular function, which is the cosine of kx. Again, assuming that this one will not spoil the structure, because I'm studying one single mode of that expansion there. So e to the I kx is cosine plus sine, no? And and this one in the Fourier decomposition, there are two different orthogonal modes. So I am choosing one of them. Notice that I chose cosine. So phi, for example, phi, then every other mode must be written as cosine. Because if I put some other mode, which will be sine, they will be orthogonal. Okay, so I had to be careful. I mean, I had to simplify, but in a good way. Okay, so yes. Right. So notice that if I introduce a cosine, sorry, then because I have a cosine, this dj will be invariant under x going into minus x. Okay, so my field will be parity even in x. So I have to make sure that all the other fields will be parity even. For example, remember that the metric looks like minus 1 plus 2 alpha dt squared. I want the metric to be also parity even, so alpha must also have cosine. If I put sine, this will be parity odd, the perturbation. Delta G will be parity odd. When I have plus 2 di chi dt dxi, now this is parity odd. So this must be also parity odd if I want the whole thing to be parity even. So again, x must be cosine, because when I do di, I will get sine. Okay? So when I do this kind of thing, I have to make sure that everything works. Delta G must be even under this. So I could have chosen sine. That's also fine. That's not. If I choose sine, that my delta G becomes now an odd function. I have to make sure that everything else becomes odd. Okay, then I do the same with ds. I do the dj0, alpha, chi, delta t, dl, phi, dr. I also put dr. Although dr does not appear in the Lagrangian, but I also set dr, because later on it will be used. Very well. Then what do I have? Then my action looks like d3 dx dy dz times square root of minus g times everything else. Okay, so now the modes don't depend on y and z, because I am supposing. So there will be a volume constant, which I don't care. And then I have integrating dx. So I'm going to do the integrating dx so that this cosine will disappear. Okay? I will have many times cosine squared, and I want that to become 1. So then I integrate between minus pi and pi. So I'm saying that the universe is minus pi and pi. It can be minus pi huge amount of quantity, you know? Okay? Whatever. Okay, so you see, I am transforming the universe into a box with size 2 pi, where I know that the cosine of kx is an orthonormal function into this interval here. Okay? And then I do the integral. Any cosine will give me 1. Every cosine sine will give me 0 into this. Okay? Then I say, look, k is positive because I am in a box. And now the Lagrangian becomes much simpler. So what happens is that we said that it is chi of time. I should put also label of k, to be honest, cosine kx divided by, I put also maybe square root of pi as to make it orthogonal. So now my action will only depend on this k of t, chi of t, this Fourier mode decomposition. Okay?